And we're showing our captions. Yes, we are. Okay. So the first question deals with what random variables are, because this chapter is talking about, so you might find some of this remind you of some of the stuff we did in earlier chapters that we were looking at, because that tends to come up. Let me bring up I had them out, but now I have it closed. Let me actually bring up the book first, because the first question has to do with what a random variable is. So let me find my share screen again and share the book so I can show you this. So the first thing that this section is going to talk about is, before we get to probability distributions, is discrete random variables. So here is the definition. It's hiding from you. It's hiding in the language of the book. So let me see if I can find that. Okay, right here. A random variable, and it's not, this definition is not given to you in the slide. She gave you what a continuous variable is. She gave you what a discrete variable is. Didn't give you a random variable. So a random variable, here's the definition, is a variable whose values are determined by chance. That's what a random variable is. And random variables can be discrete or they can be continuous. Okay. So in terms of examples of random variables, you could have the number of children, the number of, say, girls in a family of 3 children would be an example of a discrete random variable. Would be exact. Doesn't matter if they're discrete or continuous for this. This is just what it is. So it could be the number of hot dogs you sell at a baseball game. It could be the amount of the average salary of the faculty at your university. Those are all random variables. Some of them are discrete. Salary is technically continuous because it takes on values between the numbers. Okay, let me pull up the homework as well and see what we can do with that. Oh, okay, that wasn't what I was expecting. Let me see if I can go back to here. Okay, so it says, define and give 3 examples of, okay, so here, first she wants you to define and give 3 examples of a random variable. So they don't have to be discrete or continuous. You can give any 3. Okay. For number 2, we want to make sure that they're discrete random. So you want to make sure that you can count these. Discrete variables relate to things that can be counted. Continuous variables relate to things that have to be measured. Okay, so that's kind of the difference. So are we good with number 1?
Yeah.
Yeah, okay. How about number 2? Give 3 examples of a discrete random variable. Think about things that you might want to research. That this is where this comes from. things that you might want to know the answer to. So for example, if I say, let me put this, I thought this was on the screen, but I don't think it is. That should be better. So when you're thinking about examples, think about things that researchers might want to know in terms of what they're going to look for, or problems that you've actually done before. So if we look and we go with one of the things we observed before was, so examples of discrete random variables, examples of discrete random variables. Maybe it's the number of girls in a family of 3 children, right? Because I could have no girls, 1 girl, 2 girls, or 3 girls, but those probabilities differ by chance. We saw that in the last chapter. You could talk about the number of students who attend class every year at Cerritos. That's a discrete random variable, right? You could talk about, as I mentioned, if you wanted to make it specific to a particular sport, you might be talking about the number of, let's say,
Basketball games.
yeah,
Or
the
football games.
number of basketball games that, who's your favorite team?
The Lakers.
That the Lakers, let's hope they win more than last year, that the Lakers will win this season. Yeah, that works. Those are all examples of discrete random variables, okay? Because we can count these things. We can count the number of girls in a family of 3 children. We can count the number of students, and we can count the number of games they win. Now, the next thing it asks us, I think it asks you specifically about baseball, doesn't it? Next, let me see. Yeah, list 3. Okay, so here they want us to list 3 continuous random variables and 3 discrete random variables associated with Major League Baseball. Okay, so you don't have to know a ton about baseball, but knowing a little bit would probably help. But we're looking for 3 things that we could use as discrete and 3 things that we could use as continuous. So for example, okay, let's go to here and we'll do, make a line down the middle, right? So that we have discrete and we have continuous. Now, these are related to Major League Baseball. So again, you could pick
Oh,
up.
this one's number 3.
This is the 3rd one.
Okay.
Now we're all together, we're going to have 6 examples. We're going to have 3 discrete and we're going to have 3 continuous. Okay. So for your discrete examples, now these, they specifically want to be related to baseball. So we have to be a little more specific. So maybe discrete would be the number of fans, or let's say the average number of fans who attend, let's say, Angels baseball. This season, something like that. That's a variable, right?
Mm-hmm.
What else can you think of?
Dodgers.
Okay, you could go for more teams. What else can we count in a baseball, or what else might matter to the people who manage the stadium, for example? Maybe it's the number of hot dogs sold during the seventh inning stretch at home games. Something like that. That's a discrete variable, right? That's discrete. How many hot dogs do we sell? You could sell anything else. You could sell soda, you could sell nachos, whatever it might be. As long as it's something that's countable. If I go into talking about the ounces of soda that I use, or the liters of syrup that I buy, then that goes into continuous, because those are measurable rather than countable items. This could be something like the number of players who enter the Hall of Fame from this year's rookie group. So all the rookies that go in as first year players this year, the number of them who will then go on to become Hall of Fame players later, that would be a discrete variable. You'd have to have data looking back at that, and we don't know what that is right now, but that would be a discrete variable, for example. Does that make sense?
Mm-hmm.
Now, how about continuous variables?
Also, I got a question. Can we put our own answers like this on the
Yes.
answer? Because the answer keys.
Yes.
Oh,
These
to avoid
answers, and
plagiarism.
that's the other thing that happens with these. Your answers are probably going to be different than the book. I didn't even look at I'm sure the answers, because even the answers that I used in the other video, if and when you watch it later, I came up with different ones. I didn't do all 6 of these, but I talked about discrete and continuous variables, and I talked about a few. So yeah, your answers there do not have to match, as long as they're actually discrete and continuous and related to the question, they count. And I don't think she would ever ask you a question that specific to a specific type of, you know what I mean? She wouldn't restrict you. Give me 3 discrete variables related to medicine, or 3 discrete variables related to education. That's not the kind of question that she's going to ask you. She may say, give me an example, but she wouldn't restrict it to the type. So what do you think? What kind of continuous variables can you think of?
The length of a football field.
Okay, well, baseball, you mean? That, well, the thing is, that's going to be constant because of the rules, but I could say something like, how many times, or let's say the length of the length of a baseball game for the home team during the season. Because the length varies, the time, right? If you wanted to talk about the field itself, maybe talk about, how about this? The length of time it takes grounds crew to prepare the field before a game. Because that will vary too. If it's been raining or if they had a double header or something happened, that would also be continuous. So that works. The length of the actual, like the measurements are set by the rules. So those aren't really, those are actually constant. But that was a good thought, and that I wouldn't have thought of that, but that's actually constant. They don't vary, or they shouldn't vary. What else? Well, we could say, what if we said the travel time between cities when
coming to the stadium?
Yeah, that works. When teams arrive at the stadium, that works. Continuous variable. Okay, it's just trying to really make sure you remember what this is, because this gets important again later, and we do more with it in the chapter, but that's really what this is. The point of this is that discrete variables relate to countable objects. Even if you don't know how many there are, they relate to things that you can count. And continuous variables relate to things that you can to quantities, I should say, quantities that are measured, like weight or time or distance, things like that. That's the point of that whole exercise. The rest of this is more exercise driven and should be a little more straightforward to you after that. For exercises 4 through 6, determine whether the probability distribution, determine whether the distribution represents a probability distribution or not. Did you have a chance to look at the rules for this?
No, I haven't seen that before.
Okay, well, let's look at the slide. Let's go, and I'm going to stop sharing this and start sharing. Did I pull open? I don't have them open anymore. Okay, let me open it. Pull it open. All right, so here's our, oops. Okay, there's my definitions. Okay, here's my rules. Okay, two requirements for a probability distribution. Probability of each variable must be between or equal to 0 and 1. So 0 is okay, 1's okay, but the sum of all the probabilities in your distribution has to add up to 1, okay? And we can't have any negative numbers, okay? So that's what this slide is saying. Here's an example, okay? So each of these x's is an outcome. So 1, 6, 11, 16. We don't know where these are coming from. Normally you have a little better idea because you have context. But here's your probabilities. Notice each of these probabilities is between 0 and 1, so that works. And if you add up all of them, 1/7 plus 1/7 plus 3/7 plus 2/7, you get 7/7, which is 1. So this is a true probability distribution. So what they're asking us here to look at in the homework is we're going to look at the distributions and we're going to see if they follow both of the rules or not. Okay, so looking at number 4, what do you think? Is it a discrete probability distribution or not?
It would be.
Yeah, it is. But the problem here with number 4 is this negative. It looks, see, the structure's right. It's got X, it's got P of X, it's got the numbers, but look at the negative. Probabilities are not supposed to be negative, right? When we were doing probabilities in the last chapter, did we ever have a negative number?
No.
No, because probabilities are supposed to be between 0 and 1. So this one would be, you would say no. Is this a probability? No, because the probability of 12 is negative 0.8, and probabilities must be between 0 and 1. So that answer is no to number 4. Okay. How about number 5? X can be negative, by the way. X can be whatever we want, just as long as our P's are not negative. So are all of our P's okay? Are all of our probabilities okay with number 5?
Yes.
They're all okay. Now, let me ask you this question. Do all of the probabilities together add up to 1?
Let me check.
Sure.
Yes, they do.
They do. So they follow, this distribution follows both of those rules, right? So
Yep.
if you look back at the rules, let's look back here. Here's my rules. The probability of each variable must be between 0 and 1. And the sum must equal 1, right? And they do. All right, try number, I'm gonna mute my mic really quick, but try the next one.
It's cookie time.
How are we doing? Okay, let me go back to the question here.
Oh yeah.
Oops.
5's probabilities equal 1.
Okay, so do you think for number, it says number 6, but then it has number 11 next to it, but it's really number 6. They add up to 1. But here's the problem. The 3 probabilities add up to, so number 5 is yes. We decided, right? Number 5 is yes, but how about number 6?
Oh, everything is in order for the x's, but the
Right.
probability,
So the individual probabilities are fine, right?
it's no.
But this is no, because look at the probability of 4. The
And when I
probability.
added these, oh
Mhm.
sorry. When I added these all up, I got 1.9. So it looks like the
Right.
probability is greater than 1.
Yeah, so number 6 would be no, because
The probability is greater.
the sum of all the probabilities is greater, right? Yeah, you have to, in that case, you have to add the word sum to it, but otherwise, yeah, that works. So you can say, so number 5 was yes. It is a, because all of the individual probabilities are between 0 and 1, and the sum of all probabilities is equal to 1. So that works.
That's for
Now,
5.
that's for number 5. That's yes. Okay, because remember, we have to give a reason. Number 6, we say no, because the sum of all of probabilities is larger than 1. Okay,
Yeah.
so we're good with those.
Yes.
All right, cool. Do you need anything on the screen right now? Can I change the screen?
I'm still
Okay, give me a minute.
wording
Yeah, go ahead. Take your time. That's why I asked before I. Okay.
Hold on. Sorry.
No problem.
Okay.
Yeah. All right.
Yep.
Okay. So now we're going to go back, and this is going to look very similar to an exercise we did back in chapter 1. It says for exercises 7 through 9, state whether the variable is discrete or continuous. That's all we have to do. So number 7 is the number of cheeseburgers a fast food restaurant serves each day. Is that something that we count or something that we measure?
Um, what was that again?
Is that this number of cheeseburgers that a fast food restaurant serves, is that something that we count or something that we measure?
We count?
We count it, and that makes it what kind of variable?
Continuous?
No, if we count it, those are discrete. Okay. Maybe the way to think about it is here's what we're saying, because maybe the distinction is a little bit tricky. If you can count it, think of discrete as single elements. So let's, instead of talking about the number they sold, let's talk about maybe the number that somebody ordered, right? So let me do something here. Let me erase this and do that. And let me draw something here. We're gonna draw some circles that are going to represent some cheeseburgers. So somebody came in and they ordered 3 cheeseburgers. Okay. Somebody else came in and they ordered 1 cheeseburger. And then a big family came in and they ordered some junior cheeseburgers, right? And maybe a big one, an extra large one, and a cheeseburger over here. So they ordered 1, 2, 3, 4, 5, 6. Okay. My point is, these are individual. We're not talking about what happens if they didn't eat them all. We don't know, maybe somebody left some of it. If they have it, we count it as a cheeseburger. So these are discrete. Okay. Discrete, when you answer this question, you might not know how many cheeseburgers they sold. But when you answer a question with a discrete variable, the answer to that question is going to be some kind of whole number. Okay. So the number of birds in a tree is discrete. The number of chairs in your classroom is discrete. The number of houses on your street, that's a discrete variable. Okay. Those are whole numbers because they're distinct sections. If I talk about something like the temperature outside from 8 a.m. to 5 p.m., that fluctuates. Maybe it starts out at 53.4 degrees, and then it moves up to 55.2 degrees, and then it moves up to 57.8 degrees, something like that. Those are continuous. Now, I could have a temperature that was exactly, say, 65 degrees, right? But I can also take on values between those numbers, and that's continuous. That's the difference. So the number of, hold on, let's go back here. So the number of cheeseburgers that I sell, or the number of cheeseburgers that the restaurant serves, is going to be discrete. Okay. We may not know what that number is, but it's a discrete number. How about number 8? What do you think?
Continuous.
That's continuous. How about number 9?
Discrete.
Yeah. Right. That's how it works. Okay. And now we're actually going to get to the actual point of this section, which is in the last questions here, the last 4 questions or 5 questions on your homework. What you're going to do is you're going to take the information that they give you, and you're going to create a probability distribution. So you're going to take the information here and you're going to create one of these distributions. Okay. So when you create it, let me show you an example. You're going to create it and then you're going to draw a graph, I think. And I realized that the instructions are missing. So let me text her and let her know that the instructions are missing for those 5 questions. But she wants you to construct the probability distribution, and I think you're supposed to graph it, okay, afterwards. So I'll show you that. But go ahead and try and construct. When you do, let me show you one thing. Let me show you this. So when you do this, here I have, let's do the first one. The probabilities that a patient will have 0, 1, 2, or 3 medical tests performed on entering a hospital are, and there they are, 6/15, 5/15, 3/15, and 1/15 respectively. Okay. So when you do this problem, you're going to do 2 things, I'm pretty sure. I'm going to ask her right now, as soon as I get you.
Do I put it in the decimal on the PX, or
You probably
fraction?
use you can use the fraction. You don't have to convert here. What you do have to do is define your X. So if you'll notice on her examples, she has her X, and I would put next to my X, I would put equals the number of tests performed. Something like that, so that we know what this X represents. And my P of X, you don't have to define that. You just write P of X under there, and then you put your columns in there. So it would be, we're going to draw some columns in our data here. Oops. So this is going to be this. Okay. And we're going to put 0, 1, 2, and 3. Now what I'm going to do is I'm going to put the probabilities that correspond to that underneath, and I need another line. So I'm just going to put in the probabilities that they gave me. So this is 6/15. 5/15, three 15s, and 1/15. Okay, that's constructing the distribution. Now, what I need to do is I need to see if I can contact her really quick and ask her, because I think she doesn't have the instructions, but I think you're supposed to graph it, and I need to show you that, if that, because that's the next thing she does in the slides. But the homework doesn't have those instructions. So if you want to continue to construct the distributions for some of the next problems, the information is given to you. And if you want to do that, you can. I'm going to take a minute here and contact her and find out for you. Let me do a couple of things here. I'm going to stop the sharing.
So we're skipping 10 then? Until
So what we're going to do while I'm waiting on the instructions for 10 through 14 is we're going to go ahead and construct the distributions for some of the problems that are left. We did the distribution for number 10. So let's do the distribution for number 11. Says the probabilities that a bakery has a demand for 2, 3, 5, or 7 birthday cakes on any given day are 0.35, 0.41, 0.15, and 0.09 respectively. Okay, so we're going to go ahead and put that down. So we're going to say this. We're going to write, I'll come back to number. I'll come back in case we're graphing it. And I'm sure we are. So let's do the distribution for number 11. So we're going to say that X is the number of birthday cakes. The number of birthday cakes. Okay. And P of X is my probability. Right?
Yep.
So now we have our line, right? And we're going to put 2, 3, 5, or 7 where our X is supposed to be. So we have we're going to have this. We're going to have 2, 3, 5, 7, right? And then we're just going to put the probabilities that they give us underneath the respective amount. So we have, let me switch screens, new share. Let's go grab those. So we have 0.35, 0.41, 0.15, and 0.09. Okay, so we have $35, 41, 15, and 9. So we're just doing that. Now, if you were going to graph it, and I'm going to show you this on the slides, and we're gonna assume that that's the instructions. Let's see. Then what I would do, let me find the slides and show you, because that's the next thing she does. I'm going to share screen and find the PowerPoints. What we're looking at here is, see what she did? She took her distribution, right, that she created, and she made it into like a bar graph, okay? Now, when you do yours, I think hers, her screen doesn't have a, but most of the time people will draw an axis here, a y-axis, and you'll scale it by something appropriate. So like hers goes from 0.09 to 0.52. So maybe she scales this by like 10%, for example. So you would do, you pick, give me 1 second.
Oh, so I have to do that?
I believe so. Hang on. Okay, that's what I figured. All right, thank you. Bye. Yes, we have to construct the probability distribution and then draw a graph for the probabilities, which is not as hard as it sounds. It's not, these are not complex like the other graphs that we were doing. So what we want to do, let me go back to, there's a reason why I left the second part of, let me go back to number 10. Here's number 10, okay? So when we go to graph this now, we're going to draw yourself a, I'm gonna start in a different, give yourself a little bit of room. There you go. Draw yourself a horizontal line across the bottom, give yourself some space, and draw yourself a Y, just like you were gonna graph something, but just, you only need the first quadrant. You don't need all four, okay? This axis down here, the one that's horizontal, that's going to be your X. So this is my X-axis. In this case, it's the number of tests I perform. And my Y is going to be my P of X up here. And so what we're going to do is, this goes from 0 to 1. So I'm going to put, here I'm going to put 0 a little bit away from the origin just because it's easier to see it. So I'm going to label this as 0 in a minute, as soon as I make my hash marks. 1, 2, 3. Okay, these are my hash mark. So now I have my, this is 0, 1, 2, 3. Now, you can make this scale whatever feels right to you. I'm going to make it in 15ths because these fractions are all in 15ths. So I'm going to make it in 15. And I'm going to say that I have 1/15, 2/15, 3/15, 4/15, 5/15, and 6/15. And this is as far, and this is as big as your y-axis gets. So I'm going to label this out here. This is 1/15, and this is 2/15. This is 3/15. This is 4/15. I'm a little off here. Let me move my 2/15 down a bit. This should be 6/15 up here. I need to move my numbers. Let me erase this. This is going to be 5/15. And then I have 4/15. So this is going to be 4/15. It's going to be right here. And then I have 3/15 below that, 3/15. Okay, something like that, right? So now what I do is I go to 0 and I say, okay, well, 0 is 6/15 tall. So what I do, she draws bars, but what you can do on your paper is you can draw a dot above it like this. And what happens is you draw a line that's as tall as that probability. So what it looks like is this. There's a line from 0 up to 6/15. Then 1 is 5/15. So you're going to take 1 and you're going to draw your line up to 5/15 right here. And then you can draw 2. 2 is 3/15. So you draw 2 and it's up to 3/15, right about there. And 3 is 1/15. So you draw it about like this. And that's how you draw a discrete probability distribution, because it's the only value that it's taking on is those values. So these are just spires that come from them. And that's all you're doing. So that's your probability distribution and your graph. This was number 10. And she did post the corrected version of this on Canvas. So, so now, for those of you who are watching this later, the instructions will be there. Okay, but that's how this works.
Am I combining the lines like in 2.2?
No, you don't have to. Hers don't do that. They're just boxes. You're not combining them because these are discrete. So they don't flow into each other.
Oh, I accidentally did that.
Now, this is not a histogram.
Okay. I think
Okay.
that goes the same for
It goes the
11.
same for the rest of them. Yeah. So as long as you construct the distribution first, then you can create the bar graph after. So I think we did number 11. Let's see. Here's number 11, right? The question that people usually have is what scale should I use? And you can use any scale that is practical to use. So again, line across the bottom, horizontal, y-axis, right? Like so. This goes from 0.099% to 41%. So you might scale this by 5 or 10%. You'll have to go a little past 41. So maybe if you chose to do something like, here's 5%, 10%, 15%, 20%, 25%, 30%, 35%, and 40%. Now you've got 41, so you'd have to go one more to 45%, for example. But if you do that, it makes things, you can, and you don't have to be, it's not going to be extremely precise all the time. Because obviously, how precise can you be? 0.45, whoops, 4.5, then you have 0.40, oops. Then you have 0.35, and I might have to adjust these, 0.30, 0.25, 0.20, 0.15, and 0.10. Okay, you should adjust them to fit your hash marks, but I think that's pretty good. So here you can, this goes, now here you don't want to fill in the numbers that are missing because it's just these values. So 2, 3, 5, and 7. You don't have to fill in the numbers that are missing at the bottom. So this is just 2, 5, 7. And then again, 2 is 35%. So we're going to look at, I'm going to draw, here's 35. So 5, 10, 15, 20, 25, 30, 35. 2 and 35%, right about here. Okay. 3 and 41%. Well, that's just over 40. So again, don't stress yourself, but just do make it consistent with your drawing. So that's this. So we have a spire that goes, let me draw for you. So we have that. Okay. And then you have that one, right? And then we have 5, which is only 15%. So it's a little short line. Okay, 15 is about yay tall. And 9%, which is right under 10. If this is 10%, the second line, then I'm needing to go just a tad further, maybe there, right? Hold on, let me erase this because I overcompensated. So draw 9% here. So this is 10, 9 is right under here. So I'm looking at about that line. And I'm looking at something that goes, oops, it's not rolling it. Let me fix that. I'm looking at something that goes about here. And white, okay, hold on. Select, draw, line. Thank you. And I'm gonna draw in. Oh, I'm drawing in white, no wonder. Okay, that'll do it. Let me draw in the blue that I was drawing in before. Okay, so here, so something like that. Okay, and that's the way that would look. And you can put X here, X. This is number of cakes, birthday cakes. And then you have your probability of X in there. And that's it. Okay. How do you feel about the next 3?
think I could do all of them. It's just that when you made the graphs, do I like do the box like around it?
Oh, you mean if you want to make a bar, you mean like a bar graph?
Yeah.
If you wanted to make, okay, so if you wanted to make it like hers, you would make the bars, just wouldn't make them touch. So if you want to make it look like hers, let me show you that.
But this is acceptable?
Yes. Yeah.
Okay.
She only draws boxes because that's what her computer draws. But if you wanted to draw boxes instead, then I would do, just make sure they don't touch each other. So when you draw it, you do this. You say, well, my 2 is about right here. And then I draw a line down like this. And I go so that your number is in the middle of the box. Does that make sense? So something like that. There's 2, and
Okay.
there's the middle of the box. And then 3 is what? 41. So 41 is way up there. So we're going to do something like this. We're going to say This is not going to be the neatest drawing I've ever made, but we will make it work. Here's 3 like that. Okay. And then what the biggest thing is, you don't want these to touch each other because these are discrete. Okay. Number 5 is 15. So you'd get 5, 10, 15 right about here. So it would look something like this. And then 7 is 9%, which is, oops. 7 is 9%, which is right about there. Make a little bar and go like that. And if you want, you can list the heights on top. I mean, you have them listed there, so it's not, but you can list, if you like, this is 0.35. This is 0.41. Oops. This is 0.15. And this is 0.09. Right. Okay.
Mm-hmm.
So it's not, this section is relatively straightforward, I think.
Yeah. Well, now I know how to do this. I think that's it for me then.
All right, Jason, always good to see you. We'll
Yeah,
see
thanks for
you.
helping.
No problem. We'll see you again soon, okay?
All right, thank you.
Take care.
Goodbye.
Bye.